Welcome back to the lectures in Introduction to Multi-Agent Systems. In the previous lecture, we discussed how exactly the page-rank centrality works, what is the underlying logic behind it. In continuation with the discussion, in today's lecture, we'll introduce the algorithms that are actually used to implement the logic that we discussed before. Let us start by discussing the underlying logic that is used for the page-rank algorithm. We know from the previous lecture that the importance of a node or a web page which is the node in our case, is directly proportional to the importance of its neighbors. So note that this, in its principle, is quite similar to the eigenvector centrality. However, what is different is the way in which this logic is implemented. Meaning, in the PageRank centrality, we try to give more importance to the nodes to the in neighbors which have higher importance. So how do we do that? We say that each page that is there on the web should transfer its importance uniformly among all of its out neighbors. What do we mean by this? Let's look at this example again. So we see that web page number 1 links directly to web page 2. Let us consider this example again. So what we see here is that the third web page links to two different web pages, which is web page 1 and web page 2, meaning whatever importance it has, it assigns it equally to both of these web pages. In other words, the logic that we discussed here, that each page must transfer its importance uniformly among its out neighbors, could be executed in the following manner. We say that web page 3 or node 3 here in our case passes on half of its importance each to nodes 1 and 2 and 2 in this particular example. So this is specific to this example. So we see here that it gives half importance to this and half of its importance to node number 1. So in general, we write if a node K or a web page K has P number of out neighbors, Remember that the out neighbors are nothing but forward links of a web page. Then it passes 1 by p of its importance to each out neighbor. This is how the underlying logic works. How do we implement this logic? We do it in the following manner. So the PageRank update rule is given by let CPR denote the page rank of the ith web page or the ith node in the graph. Then we write it as AJI times CPRJ, but we also delete it by, so this means that jth node is passing on its importance to the ith node, but jth node will not pass on all of its importance. It will divide its importance equally among all of its out neighbors. Hence, we divide this by d out of j. Here, this is the out, this, let's write it this way, number of forward links slash out neighbors of j, and CPRI is the page rank score of the page or node I. Similarly, CPRJ is the page rank of node or web page J. Note that these are current importances which recursively get updated. So this is the simplified version of the page rank. But there are certain issues that we face when we use this version. What are those issues? Again, let's go back to our previous example. In this example, we see that the web pages 1 and 2 point only to each other and do not actually have any outgoing pages. Additionally, so this is the first point, which is peculiar about this example. Additionally, web pages 3 and 4 point to 1 and 2. Meaning now, if we apply this algorithm in a recursive manner, what is going to happen? 3 passes on its importance to 1 and 2, and 4 passes on its importance to 2. Over time, 3 and 4 keep on losing their importance, and 1 and 2 keep gaining more and more importance. Hence, during the iterations, only the nodes 1 and 2 start accumulating rank, but they never distribute any rank, meaning this is some sort of a trap that we can get into. So let's write it. Over the iterations, 1 and 2 accumulate the rank. The ranks. In other words, their scores keep increasing. But they never distribute any ranks. Implies we say that such a loop forms a trap, which is known as a rank sink. Why? We see that these are now sink nodes, right? The subgraph constructed using the nodes 1 and 2 is nothing but a sink node. Not only that, this sink keeps on accumulating ranks or the importances. Hence, in the original paper, any loop or subgraph which accumulates rank, the loops which accumulate ranks are referred to as rank sinks. Now, this is a problem. In this case, what happens is when we use the algorithm, after a while, we only get recommendation for pages 1 and 2. However, the question is that even realistic? In general, when we try to search for any topic and we go onto the web, we do not keep on a focus only on a few web pages. Generally, people tend to read a lot of web pages, which perhaps might not be recommended as the top searches by that particular search engine, because people do often get bored. So how do we incorporate this idea into the model such that we do not get rank sinks as shown here? Hence, we go to a slightly modified version of the PageRank centrality, which is implemented in the following manner. So look at the modified PageRank algorithm. It is a simple modification, but which actually makes the model quite realistic. And it's written in this manner. The page rank of the ith node let me highlight something that I've missed here. If you go back to the original equation, please note that this is all of the in neighbors of node I. Now let's continue with our modified update rule. It should be equal to this. So now we multiply, we introduce a term beta. I'll talk shortly about what is beta and how is it important. Then we do the same thing. The first part remains more or less, what is it? J. The first part remains more or less, what is it? It is, except for the newly added term, beta. And the summation is over all of the in neighbors of I. We have now a second term, which is equal to 1 minus beta times 1 by n. So what exactly is this term? Now the introduction of the second term, 1 minus beta times 1 by n, allows us to overcome the issue of the rank sinks. It will not happen when the ranks of all of the nodes get accumulated over sinks, because now we see that every time a certain rank is assigned to these non-rank sink nodes as well. Hence, the choice of the second term allows for an exploratory ranking protocol, wherein we now give chances to other web pages as well. Let's write it. Some important observations from this model is that the introduction, the addition of the term allows the system to not get trapped in the rank sinks. In turn, it allows an exploratory ranking protocol, in the sense that it allows us to now choose a variety of newer web pages which otherwise would not have appeared. This interpretation of the PageRank algorithm can also be explained using random walks on graphs by something that's known as the random. So this is also referred to as the random surfer model. So let's quickly add a few comments about the random surfer model, the random surfer interpretation. So let us consider the scenario when there's a person, or there's a surfer who is successively visiting different web pages. Different web pages. Then suppose the search engine directs the surfer to a loop of web pages or rank sinks. Imagine if we go to a certain web page and then we get trapped in a loop wherein we just keep clicking from one web page, which takes us to another, and the other web page again brings us back to the first web page. In that case, it is very unlikely that we'll continue visiting only these two web pages. Naturally, what we do is we turn our attention to some other web pages as well to get newer information, or simply perhaps because we get bored. So in this case, what happens is it is unlikely that the surfer stays within the loop, right? Eventually, she or he jumps randomly to other web pages. which is exactly what happens in the case of the new update rule. This is modeled by the term 1 minus beta divided by n, which is how the modified PageRank algorithm works. Now let us apply this algorithm on an example. Consider the diagraph shown in this figure. The diagraph here corresponds to the web page structure that we have been discussing in the lecture, which is as shown here. Just a quick recap: web page 1 points to web page 2, and again 2 points to 1, and web page 3 points to both 1 and 2, and web page 4 points to web page 1 again. Let's try to compute the PageRank centrality for this given diagram. We have initialized the algorithm with some values, some equal values for all of the nodes. You could also choose here the vector of all ones. That would also work. Okay. Let's now try to compute the centrality scores for each of the nodes. And here we are looking at the simplified centrality score to begin with. Eventually, we'll show one more example, which is based on the random surfer model. So let's start. PageRank of node number 1 should be equal to the PageRanks, the weighted sum of the PageRanks of all of its in neighbors. So its in neighbors are CPR2 plus CPR3. And what do the weights look like? So here we have not given any other web page edge weight, so we can simply assume the edge weights to be equal to 1. There's yet another weighting factor, which is given by this. Now, node number 2, as we can see here, just has one out neighbor. Hence, in the computation of the PageRank, we assign this, we divide this by 1. Let's look at node number 3. Node number 3, as we can see, has 2 out neighbors, meaning we divide this by half. What does this become? It simply is equal to CPR2 is given by 1 by 4 plus half of CPR3, which was also equal to 1 by 4. So this adds up to 3 by 8. We write the value 3 by 8 here. Similarly, let's look at the PageRank of node 2. Node 2 now has 3 neighbors, 1, 3, and 4. Let's first write up the centrality scores, and then eventually we'll add the weights. Now the weights are, node number 1 has just 1 out degree, so we divide this by 1, and node number 3 has an out degree of 2, so 1 by 4 gets divided by 2, and again node number 4 has just 1 out neighbor, so this is what it would look like. And this adds up to 5 by 8, meaning this has a score of 5 by 8. Now, what would be the centralities of nodes 3 and 4, the ranks? What we see here is that nodes 3 and 4 do not have any neighbors, hence their centrality scores simply become equal to 0. What do we get in this case? We get that we are trapped between the nodes 3 and 8. What would happen in the third iteration? If we use this model, in the third iteration, the entire centrality of node number 1 gets transferred. So let's write it here, iteration 3. Slightly to the right. We have CPR here, CPR. Okay. So in the third iteration, what we get is that the centrality scores now keep switching between 1 and 2, these values, meaning in the next iteration, 1 transfers all of its importance to 2, and 2 transfers all of its importance to 1, meaning this value here becomes 3 by 8, and they remain 0. So meaning the search engine would get trapped between the nodes 2 and 3, which in reality, of course, doesn't happen. So in the modified form, what would we get as a centrality scores? Let's try to calculate that. Let us now consider the modified update rule of the PageRank centrality, given in this manner. Here, we consider beta as being equal to 0.5 without any loss of generality. And we have assigned the edge weights to be equal to 1 by 4 for all of them, again without loss of any generality. So now let us calculate the edge weights. In this case, for the first node, what we'll do is notice that the term 1 minus beta by n given here is constant for all of the nodes. So what we can effectively do is actually compute it beforehand. Meaning, let me write here 1 minus beta, and n is the total number of agents, which is equal to 4 in our case. So this number is simply equal to 1 minus 0.5 divided by 4, which is nothing but 0.5 divided by 4, which is 1 by 8. So every node here has a centrality equal to at least 1 by 8. Okay, let's now get started with the calculation. So the first term gets multiplied by beta first, which is 0.5. And then we add the importances of all of it, the scaled importances of all of its neighbors. Meaning, for node number 1, there are again 2 neighbors, 2 and 3. The importances of node 2 and 3 are 1 by 4 with the first iteration. The importance of node number 3 is again equal to 1 by 4. And the importance of node number 1 simply gets scaled by 1. Or gets divided actually by 1. And the importance of node number 3 gets divided by the number 2, because 3 has 2 neighbors. And we have a new term here, which is equal to 1 by 8, which comes from this. And this, solving it, we can see that this simply adds up to, let's write the numbers. This is equal to 5 by 16. Similarly, let's calculate the importance of node number 2. Again, half times it has 3 neighbors, each with importance 1 by 4. And this importance, additional importance 1 by 8 adding up. And now let's quickly scale them. The first neighbor is 1, it has just 1 out neighbor, and node number 3 has 2 out neighbors. Again, node number 4 has just 1 out neighbor. So this adds up to 7 by 16. And nodes 3 and 4 do not have any neighbors, hence in their case, the only term that gives them importance is 1 minus beta by n, which is equal to 1 by 8. And let's now write up the importances. 5 by 16, 7 by 16, and 1 by 8, and 1 by 8. So this is a very important table. The reason being that what we see here is, again, node number 2 is now the most important node, which is in sync with this. So although in this case they kept on iterating, but note that again nodes 1 and 2, both of them continue to be important. And as it should be, both of them are in fact more important than nodes 3 and 4. However, through this approach, nodes 3 and 4 also get a chance to get noticed. They come up in the rankings, and any surfer would get a chance to view them as well. So the surfer does not get trapped in a loop. which would have happened otherwise in the previous algorithm. So this brings us to the end of our discussion on PageRank centrality. I'll just add by adding one more piece of information that while we have selected the value 0.8, 0.5 here in general, but in the algorithms used by Google, the value that's commonly used for beta is 0.85. Okay. So PageRank centrality, as discussed before, is one of the most popular ranking algorithms and also one of the most applied ranking algorithms. So Google search is formed out of this. In the next lecture, we'll look at yet another centrality measure known as the Hobson Authority centrality. Thank you.